All right, so we are going to talk tonight about this is Physics 1C for September 15th, and we're going to talk about how to solve some things with continuous charge distributions. When we're talking about electric potential, we're going to talk about a way to move from electric potential to get electric field by using something called the gradient and derivatives, partial derivatives, and then we'll solve some problems with that idea. And then we're going to be on talking about capacitors. You should be able to get through 1, 2, and 3 here, and we'll finish up with 4, 5, and 6 on Thursday Thursday night. So the first thing I want to do is to talk about how we solve problems like this, of which you've got a few on your homework that's due on Monday, I believe. We already started recording. I'll ask you guys later. Someone remind me to ask about the time zone for mastering physics later, like when we go on break. Time zone mastering physics. Gotta talk about that with you guys. Because I got some really strange complaints, and I want to make sure that it gets fixed. Okay, so ring of charge. How do you solve problems like this? Well, we did problems with electric fields where we had rings, and what we did with the electric fields is we basically broke the object up into a bunch of little tiny pieces, and we're going to do the same thing here. Our general idea is to find our electric potential now. We are going to have to do some type of an integral that looks something like this, k dq over r. For this one, it's going to be pretty simple. So what we want to do is to break our ring here. And let's read the problem. It says electric charge big Q is distributed uniformly around a thin ring of radius A, and we want to find the potential at point P on the ring axis at a distance x from the center of the ring. That's what we want to do. Now, the way we go about doing this, let me make this a little bigger so I can annotate better on the drawing, is that we basically take a piece of our object here. So let's take just a chunk right here out of our object. And let's say that this chunk carries some amount of charge that we call dq. All right. Now, what is dq? Well, it's a ring, so dq is going to be related to a piece of the ring and q itself here. In general, we usually say that dq would be equal to some linear charge density lambda multiplied by ds. We're probably not going to have to do that in this problem. Okay. Now, one of the great things about doing these problems with electric potential is that electric potential is a scalar. So I don't need to come to this point. Like if we were talking about electric field, right? We did problems like this. I said, oh, you got to draw a vector here for the electric field, and then you got to break it up into components, right? We don't have to do that anymore because it's a scalar. We don't need an arrow to represent what the electric field at that point is. We just know that the potential is equal to k. We can pull that out of this equation, and then the integral of dq divided by r, where r is the distance from this charge, the little piece of the object, out to this point P. We can already see in this problem that if we define x to be the distance from the origin, we're doing this on the x-axis, basically, and a is the radius of our ring, then both of these are constants in our problem, which means that we can basically just say, okay, well, a squared plus x squared square root is r, which is the Pythagorean theorem. So r we can replace right there like that. And now we look at this and we say, every point on this object would have the same value for r, right? A would be the same. This would be a. X would be the same. X is just this fixed distance from the axis, right? So these variables in the denominator, they're not going to depend on dq in any way. And we can pull them out of the equation. Like that. On the inside, then, we're just left with the integral of dq. But that is just going to be the total charge, right? What this says, you could think about this as integrating from 0 up to big Q, if you want to. And then you would understand that it's the total charge, right? Really what it says is just add up all the dq's. If I add up all the dq's, I'm going to get the total charge, and that's the total charge right there. And that gives us our answer. K times big Q divided by the square root of a squared plus x squared. And that's the electric potential of a ring of charge at a distance x away from the ring, where a represents the size of the ring itself. So there you go. Yeah, you want to ask why are your limits 0 Q? See, that makes it even more confusing, doesn't it? It makes it even more confusing if we... So, like, that's where I think, like, you should just not, like, even think about limits for stuff like this. Like, once you have this integral, and maybe this will bother you guys a little bit, I don't know. I'm not trying to... Like, once you have that integral, what does that really mean? It means to add up every single bit dq that you have, you know? So it's like, well, you sum them all up, what do you have? You just have the total charge, right? If you really want to do it with limits, what you'd want to do is you'd want to somehow get, like, you want to turn it into a length, right? And the way you would do that is you'd say, okay, well, lambda is going to be equal to... I know you're talking about limits of integration. I know what you're talking about. That's what I was referring to. You're asking why I did from 0 to q. Why'd you say my bad? I'm talking about limits. So lambda would be the total charge divided by 2 pi times the circumference, right? That would be what lambda is. And then our integral dq could become integral of lambda, which would we just pull out here. And then in here you'd have ds. Okay, what would ds represent? Well, it'd be like basically from 0 to 2 pi a, right? But if that makes no sense at all, and to me it kind of doesn't again, like why would you use 0? Then you can change the ds into AD theta. And then you can integrate from 0 to 2 pi. But all of this, I think, is a lot more complicated than just saying, when I say integral dq, I mean to just sum up all the dq's, which is just q. Either way, they all give you the same answer, so I don't want to belabor this too much. So that's the answer. Do you guys have any questions? All right. So let's do one of these with a line of charge, because I know you guys have a homework problem like this. Let's scroll up here. This one's a little trickier. So you have a positive charge Q is distributed along a uniform line. So let's get a line here. Shapes. Let's get a. So there's our line of charge. It's going to carry a total charge that we call Q. It has a length 2a lying between on the y-axis between y equal to negative a and y equal to positive a. So let's put a shape in here of an axis right here. Let's make it a different color. Let's line it up right here. Should we make it long enough? So there's our axis. This is the x-axis right here. This is the positive y-axis going up this way. The coordinate right here would be positive a. The coordinate down here would be negative a. Those are the y coordinates. Those are probably kind of hard to see, aren't they? Make it a little bigger. So that's the y-axis. This is positive a. This is negative a. Those are the y coordinates. And we want to find the electric potential at some point right here. It's being called P. I don't know if we really need to label it P. That's a distance x from the origin. So this distance is now x. So line of charge, positive charge Q. We're finding the electric potential at point P. We go through a very similar process wherein we take a piece of the object here, which I'll highlight in red. We say that it contains an amount of charge that we call dq. We connect a line from that point down to the point P, right here, and say that that line is going to be the distance r, and then the height of the little triangle we've created here, there's a right triangle, is going to be y. So dq is a distance r away. And I think that's all we need for the picture. So now what we need to do is to perform an integral. Do you guys have any questions about the setup so far? And now we just need to do this. So we're also going to have to replace dq. In order to do that, I'm going to say that dq is going to be equal to the line charge density times dy. I'm going to say that, where's the best place to put this? That this is dy. The height of this object is dy, or the thickness of this object is dy. And lambda is going to be q divided by the total length. The total length was 2a. So we get that relationship right there. And we can plug all this stuff in here and do the integral. So we've got k. For dq, we replace it with lambda dy, which is going to be q over 2a. Uh-oh, ink to shapes on. So q divided by 2a times dy. We've replaced dq now. And now what we want to do is to replace r. R is going to be square root of y squared plus x squared. And now we can pull some things out and put our limits in. So the electric potential V is going to be equal to K times Q divided by 2A, and then integral from, what would the limits here be, by the way? Negative 8a. Yep. Negative 8a. Or, like you guys said, we could pull a 2 out. And then just do the integral from 0 to a if we want to. On this problem, I'm not going to do that, and I'll tell you why pretty quickly here. Any questions, though? I went through that pretty fast. We're kind of done, actually. We're going to solve the integral, but that's the math that gets you there. Any questions at all? So how do we do this integral, by the way? Anyone know? What's a good way to do this integral? Is it trig sub? Is that right? So what do we want to sub? Something tan theta or something like that. Maybe let's start it up here. So we want to do something like y equal to tan theta. I think we need something because there's an x in here too, right? I think you need x tan theta, maybe? Yeah? That's actually this angle, isn't it? Draw out the triangle. I mean, here's the triangle, right? We've got it right here. If you call that theta, then this is true, right? Because then y over x would be tan theta. So, anyway, dy would be, what is it, x secant squared theta, d theta. And we can try to plug that in here. Now, I'm going to say I don't know for sure that this works. I think it does. I think you guys are right. But a question that someone had asked me over the week when they're working on their lab manual problems is they said, if we get to a point that we can't solve an integral or we don't know what to do with the integral, and I know for a fact there's something on your lab manual homework that's like that, where the integral is extremely difficult to do, you can definitely do one of two things. You can either look up the integral in an integral table. There's nothing wrong with that. Don't be afraid to do that. Or you can use Wolfram Alpha if you want to, assuming that Wolfram Alpha will give you an answer. Okay? You do not need to know the steps of how to solve all these integrals. This one, I think you can do a trig sub, so you might as well. Like, if you can do this, you might as well do it, if only to just re-practice your mathematical skills, because I know as you take other physics classes, as you take other engineering courses, you're going to need to know how to do this stuff, right? You don't want to lose your ability to do these integrals, because it will come up again later. All right, so if we make these substitutions here, I'm going to leave the limits off for now. What we're going to get is... so the dy becomes x secant squared theta d theta, and the denominator is going to become, maybe we can do this over here, so the square root of y squared plus x squared is going to be equal to y times the square root of 1 plus tangent squared theta. And I think that's y secant theta, right? Is that like right? Because I think 1 plus tan squared theta is secant squared theta. Oh, yeah, x. Thank you. sorry, I skipped a step there, and I probably shouldn't have. This would be x, yeah. Thank you. So this would be x. This would be x. And this is one you could think of in the following way. If you look at this picture right here, we know that r cos theta is equal to x, which means that r is equal to x secant theta, right? And that's r right there, right? Y squared plus x squared square root is r, so this is definitely true. So our denominator now becomes x times the secant of theta. Oops. And now a lot of this stuff cancels, and what we're left with is v is equal to kq over 2a. Okay, so the x's cancel, one of the secants cancels, so now we have to do the integral of secant theta d theta. What's that? What's the integral of secant theta? See, for me, that's where I'd have to look it up. I don't know. I know it involves natural logs. See, he knows what it is. That's awesome. You know that it's the natural log of secant theta plus tan theta. How did you know that, Tyler? Doesn't this same integral show up on your homework, by the way? And you have to do that, basically? So he's saying that the answer is that it's the natural log... Oh, you memorized it from 191. Well, that's awesome, honestly. The fact that you memorized this one is really cool. All right, so because this is a... I think it either comes up in your current homework or it comes up in your... that's what that becomes. They make you memorize it. Okay. That's maybe less impressive, but I mean, they didn't make me memorize this one as a kid because I don't know that one off the top of my head. I just remember that it has a log in it, is all. Yeah, but if you take... Yeah, that's funny. All right, so we have to do this, but now we also have to do some other things. We need to plug in what the limits are going to be in order to make this work. So in favor of just avoiding all of that, this is one of those things where even though it seems like this was going to work, it didn't work out so well, and we ended up with an integral that we still didn't know the answer to, right? So this is definitely a time when it's okay to be like, I wonder what the answer is, and you just go look it up on the internet, because it's a really common one. You can go and look up what... you could just look this integral up instead of getting to a point that you have to look up what the integral of secant theta is. So I'm just going to give you guys the answer for this one, because that's the way that they do it in your textbook too. They just say, here's the answer. They just say, for this... oops. Now I'm having a hard time finding it. Real quick, 1 second. Here, let me do this. Maximize... Zoom in. Okay. Yeah, they just basically say, here's the answer. So, you know what I'm going to do, actually? Just because it feels like it's going to be a little bit more quick. We're just going to grab the answer. That's the answer right there. There we go. That's our solution. It's ugly and it's complicated, but, you know, that's how these things work out sometimes. Okay? Alright. I'm doing that just to make you guys feel better about doing it yourselves when you have to do it on your homework. It's like, it's okay. If you just don't know what it is, then do this. But if it's an integral that you can work out the steps easily by doing something like a trig sub, definitely do it. Alright, do you guys have any questions? That's good. We took about 20 minutes and we solved both these problems, and they're pretty tricky. Okay, so now we get to talk about a really interesting thing about potential and electric field. How if you know the potential, you can immediately get the electric field by using derivatives. Okay? You know, in like physics 1A, how if you know like what x as a function of time is for a particle, you can figure out what the velocity is just by taking a derivative, by doing dx dt. Right, this is velocity. We're going to do the exact same thing, basically. So what we're going to do is we're going to say, suppose that I already know the electric potential. So it's like if you know what v of, let's say, x, y, and z is, how do you get from there to finding what the electric field, which is a vector, as a function of x, y, and z is? You can do the same thing if it was a function of r or a function of r and theta or something like that too. Can I show the answer one more time? Sure, that's it right there. It's in your textbook too. 23.12 is the problem. But there it is. Natural log square root of a squared plus x squared plus a, and the denominator is the same, but with a minus sign. Sure, no problem. All right, so this is our goal. Suppose that I know the electric potential. I want to find the electric fields. Okay. We actually already know how to do the reverse, because I gave you this thing that said that if I know what the electric field is, I can do an integral of the electric field, a line integral, dot product with ds, and that will give me electric potential, and this is where we're going to start from. So from here, we could rewrite this in the following way. So delta v, we could really write that as kind of like the integral of dv. But then what we could do is we could say, well, let's get rid of these integrals, because there's an integral on both sides, and we can say that the electric potential, dv, between 2 points that are really close to each other is really just the negative of the electric field dot product with ds. So then what we can do is we can say, well, what is this? Well, we know that the electric fields in general, and if we're going to write it in terms of x, y, and z, would look something like ex times I hat plus ey times j hat plus ez times k hat. Like that. Okay. And ds is going to represent, so suppose that I have a coordinate system. I hate drawing these things by hand, but, and I say this is x, and I say this is y, and I say this is z. What does ds represent? Well, ds represents, suppose that I move between 2 points from here to here. That's ds. It's a small displacement in our three-dimensional plane. So how could we parameterize or create components for this? Well, we'd say then that the small displacement ds would be equal to some displacement in the x direction times I hat plus some displacement in the y direction times j hat plus some displacement in the, dx. Sorry, this would be dx I hat dy j hat plus dz times k hat. Right? ds is an arbitrary motion, like between 2 points, and that could be composed of a small change. You could be moving to the right dx, and then you could be moving up dy, and then you could be moving, and I can't really draw this, but out this way for dz. And that combined motion would produce something that goes from the initial point out to here, which we would call a vector ds in three dimensions, right? In terms of components, we'd write that like this, or in terms of unit vector notation, we'd write that like this. So let's put these two together. Let me stop for a second. Have I lost you guys? This is all these equations and stuff. When I look at that, does that make sense to you? Any vector, right? Any vector. This isn't true of just the electric field. Any vector can be categorized by components: an x component, a y component, and a z component. That's one of the first things you learn in physics 1A when you learn about vectors, is that given any vector of some length, I can describe its x component, its y component, and its z component. And then I can write that vector in this fashion. Or I think in your, what's another way you learn this? You guys also learn this in like your, I want to say, what is it, 220? You might write it like this, right? It means the exact same thing though, right? Sorry, you guys do that, right? So can you also contrast electric field and potential conceptually at a free point? I forgot what it, yeah, at the end of this we can definitely do that. The simplest way to put it, Ash, is that the electric field is the spatial change of the spatial rate of change of the potential, the rate at which the potential is changing, not in time, but in space. All right, so you could write it either way, whatever you want to write it. This one we would write like what, dx, dy, dz, the way you guys do it in 220. Okay, so I think that's your notation. Wrote both ways, that's what he's saying. Good. So what does this become then? Well, if we write this out, this is going to be a huge kind of thing to write out here, but we're going to do it anyway. So dv is going to be equal to negative e. Okay, so what's e? Well, e is this thing. Let's just copy paste it down here, because I don't want to write it out again. That's e. And we're going to dot product that with ds. So what's ds? That's this right here. Whoops, I don't need the E part, right? Move all this stuff back. So then we dot product with this thing. And why are we doing it this way? Well, it's because like when you do the dot products in component form, it's really simple, right? This thing is going to become negative of EX dx. When I do I dot I, I get 1, right? And just to remind you, what do you do when you get I dot j? No, that's I cross j is what you get. You get k. If you do I cross j, you get k. What do you do when you get I dot j, though? Well, you take the remember how you do this? You get 0. The magnitude of I is 1. The magnitude of j is 1. And then the angle between I and j, if you don't remember it, I goes this way, right? And j goes this way. So the angle's 90. So you get 0. So anytime you do I dot j, I dot k, j, any of the ones that are different, you get 0. So you get EX dx from the first one, because I hat dot I hat is 1. Just write that here, just to remind you guys. And when you do EY dy, and you'll get an easy times dz. Oof, that looks really bad. Subscripts are kind of annoying to write on these things. Okay, so we get that. We get this, I think this is sometimes referred to as a total differential. I gotta be careful about the language I use. But when you're given something like this, there is only one way that this statement can be true. And that is if EX is going to be related to some kind of a derivative with respect to dx. And I want to explain this in one dimension really quickly. So I'm going to ignore these two, but we'll come back and we'll put them in, okay? So let's say that these two are 0 for some reason. And the only thing I tell you is that dv is equal to negative EX times dx. Well, then you could rearrange this, right? And you could say, oh, well, this is like dv over dx, and then I move the negative sign over here, and look, that gives me the component EX. That tells me that if I want to find the x component of the electric field, all I have to do is to take the derivative of the potential function with respect to x. How would that work out? Well, let me just give you an example. It says, take derivative with respect to x, and I get the x component of the electric field with the negative sign. We're going to do this in a second, but just to pull back for just a moment, the first problem we did, what is this? This is the electric potential. It's got an x in there, right? If I took this, what this equation said was, if I took the derivative of this with respect to x, it would give me the electric fields. That's what that says, right? It also tells us what electric field is and how it's connected to potential, to answer your question, Ash. Your question was, how are they connected? Well, the rate at which the electric potential changes in the x direction tells me what the electric field is, right? So to tie that back to like field lines, for example, if I had a line that represented 8 volts, and I had another line right next to it that represented 9 volts, and I knew the distance between the two of them was like, let's say 1 centimeter, and I want to find the electric field in this region, well then I could say, well, I know the electric field points from high to low, it goes that way. But I also know that the electric field is basically just the time rate of, or the rate of change in the x direction, right? Or we can make this even simpler. It's basically negative delta V over delta x. So what's that going to be? Well, it's going to be 8 minus negative of 8 volts minus 9 volts divided by 1 centimeter. Why am I writing at such an angle? I don't know. And so the value would be what? So 8 minus 9 is going to give you negative 1. There's a negative sign there. You divide by, so it's like 10, right? 10 volts per meter ends up being what the electric field is. And you might say something like, if this x, I did something wrong here. So if this x coordinate was like 0.1, and this x coordinate was 0, right? Then technically my denominator would have a negative sign on it as well, and so you get this. Oh, you're right, that would be 0.01, wouldn't it? I'm going really fast here, so this would be 100. Thank you for noticing that, I appreciate that. Yeah, you're right, it's not super important, but I thank you for, because people might have been confused. So does that make sense? That's all it is. It's just like, it's like delta V over delta X. That's how you do it. It's literally, that's what that means right there. Any questions? Potential is energy per unit charge. Electric potential is energy per unit charge. I don't know if that answers your question. Or this is really what it is. It's the line integral of E dot ES. I don't think that tells you much. But... Okay, let me just move this stuff off to the side so we can keep doing the problem. Alright. So now that we see that the derivative with respect to x gives us EX, we can actually expand this out more, okay? And what I'm going to do is, I'm just going to say, suppose that we want to... Let's move this over here too, so you can have it on the notes or whatever. But so now, in general, the way we write this is that dv, okay, should be equal to the EX. Now, what we really want to do is we want to replace it with a partial derivative of v with respect to x. This is probably going to start looking like something you've seen in your math text before. For this to be true, then EY must be the partial derivative of E with respect to Y. And I'll define partial derivative here in a second, but it's really just a derivative with respect to Y. And then EZ needs to be the partial derivative of... yeah, EZ would be like this. And of course, the negative sign comes inside of here too. So really, if I want to do this properly, what I have to say is like this. Now you're going to have negative, negative, negative. And then it works out. Oh, you know what? Actually, I don't want to confuse you guys too much, but this is what you would do. That way it'll work out. Because then the negatives cancel out with this negative and you get a positive. That's how it needs to work. A dy? What do you mean? Oh, no, sorry. Yeah, that's a z. That should be a z, I'm sorry. Thank you. I didn't notice that. Yeah, thanks. There you go. That is a dz. So what does this tell us? This tells us that, in general, the electric field component in the x direction is found by this term right here, negative del v del x. The y component of the electric field is found by this term right here, negative del v del y. And the last one, the z component of the electric field, would be equal to negative del v del z. And that is our relationship. And we can write it in a more general form. There's a negative sign. So where does the negative sign come from? Okay, I'm going to take this back to Physics 1A. The negative sign here, okay, the negative sign here comes from the fact that there's an inverse relationship, not inverse, there's kind of a negative sign relationship between potential energy and work. It comes from this. Work is equal to the negative of the change in potential energy. That's why. That's where it comes from. Just like gravity. Yep. When gravity does positive work, it pulls things down, right? When gravity does negative work, that's an object being lifted up and increasing its potential energy. So there we go. That's our relationship. If I want to find this thing, I need to use this partial derivative thing. So what's a partial derivative? So a partial derivative, and we'll do a little kind of like just a completely silly problem. Suppose, so if v as a function of x, y, and z was given by, let's say, let's say that was our electric potential, and it had the proper form or whatever, right? Then I could find individually each one of my components, right? I could find each one of my components by doing this process. So what does it mean? So first of all, we'll just calculate what del v del x is. So what this means when I say partial derivative, and it usually has these like curly d's instead of like the difference would be, this would be a full derivative, complete derivative or total derivative, or what do you want to call it. This is a partial derivative. This says to hold every variable except for x constant and only take the derivative with respect to x. Okay? And the derivative with respect to x for this problem would be, suppose that y does not depend on x, suppose that z does not depend on x. They're just coordinates. To take the partial derivative, you just take the derivative with respect to the variable x. So what would that be? What would the first part here, what's the derivative of the first term? Or you guys can type in the chat, what would the partial derivative with respect to x be for this equation? The first term is 6y squared. What's the second term? 2z squared. That's easy, right? Because it's x to the first power, right? That's del v del x, right? Okay, what's del v del y? You guys can write it in the chat too if you want to. This says to only take the derivative with respect to y and hold all other variables in the problem constant. So you're going to get, the first one is going to be, bring the 2 down, yeah, 12xy. And then this one's going to be 0, yeah, so plus 0. And then we've got, because again, you hold every other variable as a constant. You don't just ignore them. There's no y, so del v del y is like, this would be like taking the derivative of 2 or something. It's not z squared because we're taking del v del y. Oh, the first part, yep, that should have been cubed. That's what you're talking about. Yep, thank you. And if we do del v del z, only one term has a z in it, so this would be 0 for the first term, and then 6z squared, with an x, I think. 6z squared, and you leave the x there, just as if it was a coefficient. Okay? I think a lot of you might have taken, whatever, 220, where you learn about these things, but even if you haven't, I think the idea of a partial derivative shouldn't be too overwhelming to you, I hope. Because the process, at least, by which you do it is pretty straightforward. So, what's our electric field, then? Well, the electric field, would be EX, which is this thing with a negative sign, right? So negative 6y squared plus 2z cubed times I hat plus negative 12xy, I'll probably run out of room here, times j hat plus 6z squared x, also with the negative sign, multiplied by k hat. And that's our electric field. It's pretty easy, right? The point is that if you know this one, you can immediately get to here. That's the whole goal of this. That's what we were trying to do, is to figure out, given v, how do I find e? And that's how you do it. You just take a derivative. In this case, it's 3 derivatives, but, you know. Sometimes you'll only need to take 1 derivative, actually. We'll see that later. So there's a simpler way to write what I wrote here in the boxes. And I think some people were already mentioning it in the chat by using a symbol from vector calculus. So the other way to write it is like this. There's a symbol that's called the gradient or nabla, and it's an operator. And what it does is you write this basically: del x times I hat plus del y times j hat plus del z times k hat, and then that long expression that we have kind of right here. Well, where's my cursor? I lost it. Right there. Then we can just write it like this. The electric field is equal to the negative of the gradient. They call this the gradient when you just operate on a scalar field of v. That is a very nice, simple way to put it. E is equal to the negative gradient of v. Hey look, Jose actually put that symbol into the chat. How did you do that? Did you do that with LaTeX, or did you copy paste it maybe? I don't know. Copy paste, yeah. Cool. Yeah, people don't always draw the arrow above it, especially in textbooks, because in a textbook what they'll do is they'll use like the bold E, and then this to like they use bold to represent vectors or whatever. But so yeah, electric field is the gradient of potential. The last side example. You mean go back to here? This one? Miaris? This one? Okay, sure. Oh. Here? Or the one on the side, like, to the right? Okay. Right here? This one? Any questions about this? Okay. So, let's tie this back to the first problem we did. Let's actually do this for this problem. So the negative is, yeah, you gotta figure it out, but it's like you do 0 minus 0.1. Yeah. 8 minus 9 in the top, 0 minus 0.1 in the bottom. Alright, so now we do this other problem, which should be able to find somewhere over here. We'll do this one first, and then maybe we'll do the point charge too, just to show you how that works out. So, we proved in the first problem we did today, example 23.11, that for a ring of charge with radius A and total charge Q, the potential at point P on the ring's symmetry axis at a distance x from the center is this. Like, that's the first thing that we did. Now we want to find the electric field at point P. Okay? According to what we just wrote, what we need to do is to find the electric field, the x component, we just take the negative partial derivative with respect to x of the potential, right? So what we're given here, this is basically the electric potential as a function of x, and we can find the x component of the electric field, only the x component, by the way, that we find by doing this, by taking the negative partial derivative of the potential, v, with respect to x. So, plugging all this stuff in, we're taking the derivative of this, right? So, do I need to rewrite the equation? So what's the derivative of this equation going to be? Well, the q and the 4 pi epsilon naught are not going to change, right? So I'm really just taking the partial derivative, and there's a negative sign, don't forget that, of 1, or I mean I prefer to write it like x squared plus a squared to the negative 1/2 power. So that's the derivative we want to take right there, of that whole function. Can you guys write in the chat what the answer to that would be? What's that derivative equal to? Take your time to write it out. Okay, so you bring down the negative 1/2, as Ash is saying. And then you rewrite the function. And then you subtract 1 from the power. That's it, right? Oh, one other term. Times the derivative of the inside. Chain rule, thank you. Times 2x. Yep. There we go. Some things cancel out, and we end up getting e sub x is equal to negative negative cancels, the 2's cancel. You're just left with 1 over 4 pi epsilon naught. Sorry, it's q over 4 pi epsilon naught. There's an x, and then in the denominator, there is x squared plus a squared to the negative 3/2. Now, we already did this in a previous problem, but it's kind of nice to see an application for something we've done before. We already proved this back in the first chapter, I believe. But now we've done it in another way. It's always nice to be able to prove something in 2 different ways and show that you get the same answer, right? So here's a question. Well, okay, do you guys have any questions? Yeah, that's right. The 3/2 should be, that's right, thank you. I appreciate that, Mr. Miars. Yeah, this would just be to the 3/2 now that I moved it down here. Thank you so much. Yeah, otherwise, it doesn't, okay, any questions about this? Does this make sense? Okay, so here's a question. do you think that we can find, like, the y component here? We know that the y component, we just take the y derivative, right? You get 0. Now that's true, right? It's true. But there's no y variable, that's why you get 0, and you get the same thing for z. And now we have to think, okay, a ring of charge, does it make sense that the y component of the electric field is 0? Let's go back to our picture. It does, as long as we're on the axis, because the y components cancel out. That's exactly right, Ash. And the z components would too. So that works out well. But one thing to be careful about is, because there was no y that showed up in this equation right here, we can't be certain this is true everywhere in space, right? So for example, if we instead looked at a point that was, let's say down here, for example, we'll call the point Q. No, that's bad. That's a bad choice, isn't it? Call the point like P2 or something. At this point, our equation isn't true anymore, right? At this point, you'd have to redo your integral for the potential, and it'd be quite complicated, honestly. You can try to do it yourself if you want to. Now, if we did that, our equation would have a y-coordinate in it, and we might be able to get an equation for, in general, what the electric field in the y direction was. But we only know that this is true at point P. It's not true at other points. Other points you choose, you're going to have y components. And be careful about taking this idea too far, is all I'm trying to say. Sometimes you just don't have enough information to just take the derivative. And you know, you can't assume that this means that this is the answer for any point in space, x, y, and z, and then be like, oh, that means that EY is 0 everywhere. So just be kind of careful about that. It is 0 at this point, though. That's for sure. Do we want to do this for a point charge? Do you guys want to do the way this works out for a point charge? Ow. Man. We can do the point charge pretty quickly. So what's the electric potential for a point charge? For a point charge, we know that if I have a point and I say it has a charge Q, and I come out to here and I say, what's the electric potential at a distance r away? We know the answer is it's basically just K times Q divided by R. So now can we use this to figure out what the electric potential is? Well, I didn't mention it, but one thing we can do is if it's a radial symmetry, we could say the ER, the radial component of the electric field, you can probably guess you can get by just doing del V del R. And you'd be right. So if we do that in this problem, what do we get? Well, if I take the derivative of this one, what do I get? K and Q are constant, right? So this is easy. Oh, whoops. You know what? I did something. Oh, no, it's okay. We're just talking about the R component. Yeah, we're good. So what would the R derivative of KQ over R be? You're really taking the derivative of 1 over R, right? Negative 1 over R squared, right? So the negatives will cancel and you'll just get, not surprisingly, KQ over R squared. That's the radial component, right? And that's exactly what we would expect, right? What if we wanted to do it using X, Y, and Z? What if I wanted to take this and I asked the question, okay, well, I could see this, that's great. That doesn't surprise me at all. But what if I want to find the X component of the electric field? I'd have to do negative del V del X, right? And now is where you kind of need a coordinate system. Like, okay, this is X, this is Y, and Z comes out of the page. And R is some arbitrary point that has coordinates X, Y, and Z. How would I find del V del X if I just look at that equation right there? Convert R into components, yeah. Well, so you could say if R is a vector, then we would say R is equal to X I hat plus Y J hat plus Z K hat. And R in general, what would little r be equal to? What's the magnitude of it? Use the Pythagorean theorem, right? X squared plus Y squared plus Z squared. then we plug this into here. So now our electric potential function, as a function of x, y, and z, would be and now we can find Ex and etc., right? Let's do that kind of quickly. So E sub x would be negative del v del x, right? We take the x derivative of this. What do we get? I believe what you're going to get is k times q. You have a negative 1/2 that you have to bring down in front. You're going to get a 2x from the inside, and then you're going to get x squared plus y squared plus z squared to the 3/2 power. And so you really get Ex is equal to, the 2's cancel. Oh, whoops. There's a negative sign overall. When there's an outside negative, and there's a negative from the derivative of the denominator. So the 2's cancel, and you basically get k times q times x times this whole thing. And that's the x component of the electric field at any point in space around the object. You take the x coordinate, you take these things, that gives you the x component of the electric field. Now, that looks really ugly, right? We can repeat this process for all of them, and to save time, what I'll do is I'll just... it didn't work as well as I thought it would. I need to stop writing at an angle. Let's move that up just a little bit. Did that work? Yeah. So if I want to get this for the y component, all I need to do is to replace the x's. Oops. Lost our 3 here, lost our 3 here. If I want to get the y component... Oh, negative 3/2 power. Oh my god. Thank you so much. Negative, 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 negative. Thank you for noticing that. This would be kq times y, and then this one would be kq times z. And that's e sub y. Okay, so we get that one, we get that one, we get that one. And now if I want to put them all together... Oh, that's a z. I know that, as I said before, the electric field is basically equal to Ey times I hat plus Ez times J hat plus E... Yep. What am I doing? Losing my mind because I'm going too fast. Here, let's erase Y, Z. Okay, it would be Ex, because that's the I one, and then Ey, because that's the J one, and then Ez, because that's the K hat. Right? And now I can put everything together, right? All of those things together. And what I'm going to get is something like this. They all have the same denominator, and they all contain KQ. So KQ divided by... Oh, that looks ugly. KQ divided by... And then I'm going to have... This one has a y in it, this one has an x in it, and that one has a z in it, and I just multiply those things by this. So it's going to be xi hat plus yj hat plus zk hat. And that would be, this would be the electric field as a function of x, y, and z. Oops. X, y, z. Okay. Now that looks pretty ugly, right? I mean, there's a reason why when we talk about electric fields of a point charge, we usually talk about radius as opposed to x, y, and z, because this is a much more compact way to write the exact same thing, right? But nonetheless, we can pull it out of here actually, and show that it's the same thing. What is this term right here equal to? What is xi hat plus yj hat plus zk hat equal to? It's r, right? Yep, that's r. And what's x squared plus y squared plus z squared to the 1/2 power equal to? Or to the 3/2 power, however you want to put it. Oh, this is r with the vector symbol. That's important. What's x squared plus y squared plus z squared equal to? It's r squared, right? Yeah, okay. So this is r squared. And now it's to the 3/2, right? And we've got our kq. This would be the electric field, right? And we can simplify it. It becomes kq times r divided by r cubed. But there's a relationship that says that r over r is equal to what? If I take r divided by the magnitude of r, what's that equal to? Unit vector, r hat, right? So that then this basically becomes kq over r squared again times r hat equals e. We're back to right where we came from, to right where we started with. So there you go. Do a lot of, the electric fields of a point charge is something we've done a lot in this class. I don't know how much this stuff is interesting to you guys, but it's pretty cool that you can write it in terms of x, y, and z now. This is something we wouldn't have been able to do before, not very easily, right? It would have been a little bit harder to write the electric field in terms of x, y, and z. We'd have to do some trig. Maybe it wouldn't be that hard, but I think it's kind of cool that we can write it in multiple ways. You know, you can write it like this. It's, you know, long and complicated, but maybe it's useful in certain situations, or you can just write it like this. You know, and you know, different versions are going to be useful in different positions, right? Like if you're coding some program and you need to code electric field into it, or gravitational field, or anything else like that. You know, it may be easier to code it in with x, y, and z components as opposed to coding it in with r components. You know, using 3 numbers for r instead of just 1, because that allows you to define, you know, specific points in space more easily in a computer program than it is to use something like this, where you have to start introducing angles and stuff like that as well, that wouldn't be automatically defined without parameterizing it like x, y, z. Okay, a lot of vector calculus we just did. What? Repeat what? Can I repeat? Y parameter. Oh, parameterize? I'm honestly probably using that word wrong. What did I say? What did I say with parameterize? I think what I meant was find components, is when I said that. I think that's more properly what I mean by that. Is find the components is kind of what I mean. Like, why did I say parameterize? I guess I'm thinking about, I don't know what I'm thinking about. It's late. Parameterize. Why did I say that? I was like, parameterization is like where you have a curve that's like a t parameter, right? Yeah. And that's not really what we're doing here, but you are taking a function of r and you're rewriting it as a function of x, y, and z. So I guess it's not, you're not really parameterizing it, or am I? That's not happening. I shouldn't have said that. All right, do you guys have any questions? I am going to pause the recording right now.